Hi, I'm Kumar. I have a broad responsibility across the campus products, which mainly dominated by access points, PoE switches, and to some extent even the campus leaf spine switches or the campus aggregation switches, depending on what terminology you use. So the couple of concepts that we want to introduce here, there's something called MSS-G. I'll get straight into it. The concept behind MSS-G is typically when we want to attach policies to endpoints, we first put them in some kind of a VLAN and then we attach policy to that VLAN. So it's kind of policies that are actually attached to the VLAN versus actually to the device. What if the device moves, then you have to again transport all the policy to that VLAN that goes in. So this is a typical, I'll just play it out here in the interest of time. So basically, we introduced this segmentation concept because the way we want to do this policy attachment is as a device comes up, you profile the device either as part of the normal authentication process or whatever other mechanism we use. And this is where some of the Arista integration with the NDR also comes into play. And once we know this device is a camera or whatever, then we automatically can say that this device is part of what we call as group A, and this group A can actually talk to only group B and C. And this makes all the more sense when we have IoT devices. If I have an IP camera, really it's doing three things. For most part of its life, it's recording into a DVR. The second part is probably taking some control information from the administrator to pan and zoom, or even less rarely, it's actually going to the internet to maybe look for some firmware upgrade, right? So we kind of know its behavior, and knowing that, I can actually box this device into saying that it's only these set of groups it needs to talk to, right? So this is a concept that we introduce where we can decouple the policy from having to live with the network constructs. Instead, you actually attach to the device, whether the device moves from VLAN A to B to C, moves from one location to another location. We have same way of attaching this policy. What I'm giving is only a high-level view. There are a lot more into it. Basically, it can actually query the CMDB and get some information about this device so that irrespective of where this device is located, even if the security camera moves or the IoT device moves, we can actually make the policy follow that particular device. The concept that is driving this whole MSS-G is actually also making what we call the TCAM ternary content accessible memory TCAM friendly, right? Typically, when you start putting large ACLs, no matter how much technology we have gone forward in terms of switching, TCAM resources is always a problem. Whereas what it does here is because it basically puts it into different kind of groups. All I have is a group to group permit or deny. Typically, if you look at it from a whitelist perspective, devices are allowed to talk to group A, B, and C, but not to all other groups. It's very easy to actually put this rule. Why even bring this up here? Because fundamentally, in most of the enterprises, if you see, they do prevent the traffic to be locally bridged between two devices, mainly because a lot of them want to have at least some semblance of understanding of what devices came in, generate some kind of flow records for forensics and whatever reasons. So in this scenario, what happens if we take advantage of the fact that the traffic flowing from the devices, when it hits the switch, we can actually apply this policy in a very consistent way, whether the device is directly plugged into the Ethernet switch or whether it is coming through the access point, we are actually able to apply the policy in a very consistent way. This is one of, yes, please.
Can you refresh my memory? What's MSS-G?
Macro security segmentation by group.
Thank you.
There's a whole concept called MSS. This is a group element of the MSS-G, which is specifically we adopted for the campus access network. Yes, please.
Yeah, just as a comment, taking something that is already a three-letter acronym in networking like MSS and then applying it to one of your concepts, that's just going to confuse everybody. MSS is a thing, and it's just going to be like, that's why I'm getting.
Okay, so fair enough point. I don't have immediate answer as to how we will address, but we'll definitely address that. I think it's
or worst comes to worst, and that's for non-native speakers. Always spell out maybe at the bottom of your slide.
Yeah, no, I actually put it in the beginning. I didn't spend too much of time there.
Yeah,
there it is.
So we did it.
Thank you.
I just moved on too fast. Sorry about that.
In fairness, IEEE did the same thing in the standard. So
Fair enough, but I think your point is noted. I think it would not hurt us at all to call out what MSS-G in each of these slides. So we'll definitely do that. So yeah, so the whole notion is this is again goes to the openness, right? The reason we are actually able to apply this policy consistently, whether it's a wired directly attached device or coming to the AP, is because fundamentally there is no mumbo jumbo protocol of putting this packet into that packet and munging some headers type of thing happening. What is coming out of the access point is exactly an 802.3 Ethernet packet with the 802.1q VLAN header. Boom, you go. You apply the policies exactly the same way. So this is a concept that even though it happened for the switch, you are actually able to apply broadly for not just only for direct attached devices on the switch, actually able to apply it across all the campus devices that are coming through. In the last MFD, or maybe one before, we briefly touched on this architecture. So just to quickly refresh, the main Arista Wi-Fi architecture has three components. There's management, whether it's on-prem or cloud. Most of the customers are cloud-based customers. There are a few on-prem. There is a data plane. We are not dependent on, let's talk about the control plane. We are not dependent on a controller for the control plane. The control plane is a distributed algorithm that is running among the APs. We have a little bit more details in the next slide. The good thing about this is, even if for some reason there's a momentary loss of connectivity to the cloud, you may not be able to make new configurations, but roaming and all other events just happen fine. There's absolutely no dependency. And finally, when it comes to the data plane, we actually have two modes. One is local bridging. I think we just saw in the previous picture also. That is basically the AP is putting out a simple Ethernet packet. But we also have what we call as a tunnel mode for the AP. And the best part is, we'll talk about more in a little bit more detail, but the tunnel or the local bridge decision is on a per SSID basis. So you don't have to dedicate an entire AP, trombone the traffic to one location of the network, and then bring it back to another network location and so on. So we have a corp ID, guest ID, contractor ID. Maybe you choose to locally bridge all the corp SSID because that just enjoys the same policy as the rest of the network devices. You may choose to put the guest and take it close to a firewall where you can just look up the flow and send it to the internet because that's really all you want to do with the guest. And maybe for contractor, they are dedicated to a set of servers, and you may take it into a point in the network which is close to those servers. So anyway, what I want to bring out here is three things, right? The data plane remains very flexible, and this is actually what is allowing us to go into some of the brownfield deployments, which are today controller-based. We're actually able to replace the controller without having to worry too much about where the control plane is going to run and so on, because the control plane is actually distributed protocol running among the APs. So this is the distributed control plane. This is one of the innovation that we got pretty much from day one. So the whole notion of this control plane here, and I'm going to skip through this in the interest of time because I want to cover a few other slides. This is a distributed protocol that is running among the APs. The whole concept here is, each AP is able to identify the radio neighbors, and instead of depending on a controller to maintain all the states and then tell the new AP where the client is roaming to, basically, as the users are roaming, identifying the radio neighbors and being able to transfer the state securely between those APs is really what this whole distributed control plane is. And just to case in point, we have a deployment in a hospital, in a live clinical deployment, where we have close to 6,600 APs working through this distributed protocol. So there's no inherent scaling issues with this kind of model. And again, in the breakout session, if you want to dwell deeper into it and see, understand a little bit more deeper, happy to go into more details there. Hopefully this answers your question on where this tunnel is terminated. So really what is happening here is the access points are connected to a campus leaf, campus spine, and just one of our switches basically becomes a tunnel aggregation. The reason we are able to do that is the protocol that is running between the access point and the tunnel aggregation is nothing more than a simple VxLAN. So we are actually able to bring to forth every hardware capability that we have put in. I'll talk a little bit more about what those hardware capabilities are. But at the outset, what we get is basic multi-chassis lag. MLAG stands for multi-chassis lag, where I can take two chassis, make it look like one logical entity. Really what is happening here, if you do not want to define all the VLANs on each of the access switches, and if that's how the network is already architected, it's actually working in that way, by all means, remove the existing controller, put a pair of Arista switches, and off you go.
So everything we're seeing is Arista. What if I don't have Arista in the LAN? What do we do?
There is zero problem, and I'll explain with a little bit more detail. Any switch which can do IP forwarding will be able to take the VxLAN packet. So the access switch can be from any of the other vendors. We really don't care. What about the aggregation switch? Same thing. It doesn't matter because all we are sending is basically a VxLAN packet, which is exactly like an IP datagram, no different. What happens if the tunnel aggregation is not an Arista switch? Of course, we would like to recommend Arista switch. Really, what it's doing is it's terminating VxLAN tunnel. So if you have a switch from a competitor which can do VxLAN tunnel termination, plus one more functionality, and just hold on 30 seconds to understand what that functionality, again, it's nothing esoteric. It's what we call as VxLAN to VxLAN bridging. If you can do that, any third-party switch can actually do that function. There is no Arista-ness to any of these protocols. It's completely open from that perspective. Okay, so we talked about the flexibility. It's per SSID, per AP. You can choose to take each SSID either in tunnel mode, and you can take to different points in the network. It doesn't have to go to the same tunnel ID. High availability, because fundamentally the MLAG itself is redundant, but you can actually put two MLAG pairs if you really want to, because each AP is set up to have an active and a standby tunnels which are actively pulled. Scale. Each tunnel aggregation switch, the low end we support 4K APs, not 4K tunnels, 4K APs. So you can have 16 SSID per AP, no problem. There is no as many VLANs as you want. It's just the number of APs. Going up to 8K, these are on the campus switches. But if you really want to go beyond that, we have some what we call as a SAND or the Jericho-based switches, which actually support that. Yes, sir.
So that last line, you don't have to be an EVPN expert. Okay, fine. Is CVP acting as a controller, or is this EVPN? And if so, what happens with EVPN convergence times if you have a fast roaming client? Because I know that's probably the path.
Excellent point. First of all, between the access point and the tunnel aggregation, we do not run EVPN.
Okay.
What we are running is just VxLAN encap decap, so that we can transit an underlay network.
But if I roam from one switch to another switch, and I'm relying on EVPN to converge, right? Because I mean, we are abusing BGP horribly in this. What kind of convergence times? What guidance do you give customers who are worried about people who are walking quickly through a building on a phone call?
Again, fantastic question. What happens is, let's say you moved from AP on the left side to the AP on the rightmost side. Just roam from one AP to another AP. The convergence for the MAC address move happening from AP1 to AP4 is happening at the data plane learning rate on the tunnel aggregation switch. The MAC address of the host that moved from AP1 to AP4 is advertised northbound using EVP and BGP from the tunnel aggregation switch. But from a tunnel aggregation switch northbound perspective, that MAC has not moved.
No, I understand, but when you move from one switch to another switch.
That is happening at the data plane learning rate. It is not driven by EVPN control plane. That is why we didn't run EVPN between the access point and the tunnel aggregation. It's just VxLAN. So what is really happening is, from the tunnel aggregation switch perspective, it was taking the MAC till T0 on VTEP A. I moved to AP4. It is now seeing the same packet on VTEP D, and it learns exactly at the data plane rate. It now sees this MAC, boom, age it out, learn on this one. The time that we have seen is typically of the order of low single-digit millisecond at that point for end-to-end. I'm not talking about the learning. The learning happens much faster.
But if it's even when it's a different tunnel aggregation switch?
Even if it is different tunnel aggregation, if I move from one AP to another AP in a different tunnel aggregation switch, EVPN is involved. At that point, what we have seen is with few hundred MACs churning at any given time, like there's a constant churn of few hundred MACs between the switches. It typically takes of the order of few tens of milliseconds for those convergence to finish.
So if the user is mobile and they are engaged in a multimedia application like a Teams call or a Zoom call, they may be impacted.
So on the Teams Zoom call, let me answer that in two parts. Empirical tests have shown we are not dropping any packet, number one. Number two, what happens is all these teams Zoom, they use something called HTTP ABR, adaptive bitrate. Because these are driven by fundamental HTTP transactions for small chunks of video at any given time, as I am moving from even going from one tunnel aggregation switch to another tunnel aggregation switch, as long as that journey completes in the order of tens of milliseconds, I don't see any disruption. Yes, I might see just a one frame blip when I go from one to the other, but I don't lose the session, I don't drop the session, none of those things happens. The second point I want to, as a practical point I want to bring up is, at least from all the customers who have deployed, because we support 4,000 to 8,000 APs on a single tunnel aggregation pair, so far, even roaming, even the 6600 APKs that I talked about, they have broken it into sort of 4 domains. So there are like 4 domains which are 1,500 each, is covering some set of buildings and whatnot. And given the limit, scaled up to 4K or 8K APs terminating on a single MLAT pair, it provides enough headroom for them to grow, even if the 1,500 goes to 2,500, 3,000, 4,000. And the future versions of these switches that are coming up, which are Trident 4 based mechanism, they already support 16K virtual ports, or 16K APs can tunnel to a single switch.
Okay, I gotta ask, do you have a customer with 16,000 APs on one campus?
No, we don't have a customer with 16,000 APs in a single campus. The largest I have seen so far in a single campus is about 6,600, 6,700, somewhere in that range. There is a university deployment that we are currently going through, which is about 25,000 APs. But from what I understand, they don't expect that 25,000 APs to be part of sort of a single flat VLAN or a single flat control domain, right? It's broken into 4 domains, actually.
In this case, particularly John was talking about roaming. Why? It seems to me that OTA would be a better option for roaming in this situation if we're going to add up that delay going back to the aggregation point and coming back. Do you guys have an option for OTA, or are you guys is everything on the wire?
This is completely on the wired at this point. So, in fact, that's precisely one of the reasons we didn't want to pull the entire EVPN and BGP capabilities into the AP. There's enough horsepower to run it, but we didn't want to do that.
This is required only if you want to tunnel the traffic to an aggregation point. If you're going to do local without, that's entirely OTA. That just happens in a normal sense.
Okay.
This is only when you want to take the data to a termination point.
That's a good point.
And you said this works on non-Arista hardware?
Yes, so the campus leaf can be non-Arista hardware, no problem.
But the aggregation has to be.
The campus spine has, okay, so we'll go to that. We'll talk about this and then we'll go back to the previous slide. Why we say we prefer Arista hardware. Because what happens is, you're coming on this blue VTEP and you want to go out on the red or brownish amber VTEP. Why do we need to do this? Because if you want to print from a station to a printer, whatever be the case, in this scenario, most of the switch fabric that we know of, when an ingress VxLAN packet comes in, they consume the VxLAN header and they think they only need to forward the inner packet to the outside world. What we have actually done here is, that's where the kind of the pin is showing here, that loop back. What we have done here is actually we have enabled the hardware to decap on the ingress and encap in the same processing, so the packet can go back to another AP on a different VTEP, potentially even on the same VTEP. So as long as this hardware capability is there, feel free to put any other switch, no problem. And this is nothing esoteric, it's just packet came in with VxLAN header VNI equal to 5, came in with the IP address A and B, that needs to turn around and go with IP address B and C. That needs to happen in hardware. That's really all that we are asking. You could do it in software, but obviously you're going to give a performance in a big way.
Oh, actually, I have one there.
Yes.
So my environment supports a lot of VO Wi-Fi. Do you guys support multicast through VO Wi-Fi?
Yes. So actually,
I know it's a basic question, but it's relevant, I promise.
absolutely relevant, and that's why I actually formulated this problem here, because it's not like anything has two sides, two sides of the coin. So for all the convenience that we get, there is a scale issue that we see here, right? Because fundamentally, 4,000 APs, 20, 25 clients per AP, you're going to see about 100K MAC addresses totally on that side.
Yeah.
What are you going to do about broadcast, multicast?
Yeah.
Absolutely valid question. That's the whole concept that we are here. There are some mitigating factors. Typically, at least we see two different VLANs. There's the corp VLAN and the guest VLAN. So that reduces the broadcast domain a little bit. Most of our customers do 4 to 6 VLANs at the edge, sometimes going up to 10. They don't want to obviously pull hundreds of VLAN there. So that gives another level of mitigation. Further, and this is where we take advantage of some of the EOS capabilities that come in. So if you really look at the two parts of this table, there are some optimizations in the AP that are generic, but more importantly, what we get from the EOS and the hardware, switch hardware capabilities. One is that basically in a lot of scenarios, people don't want to just send it back to another AP. Maybe it's a guest SSID, you just want to send everything northbound, right? You just turn off the VTEP to VTEP bridging. There's all kind of rate controls for broadcast multicast, how much rate you want to push down. MDNS proxy there to dictate what VLANs the MDNS clients are and which are allowed to see the MDNS servers on a different VLAN. We have a proxy for ARP IGMP neighbor discovery. So an ARP request that is coming into the tunnel aggregation switch is responded to locally in 99% of the case. Radius RADSEC proxy, we do not expect you to define thousands of IP addresses into the AAA server. You can actually choose to define only the tunnel aggregators IP into the Radius server. So those are the optimizations that EOS is providing, and we are actually doing more, right? These are something that are already there. I just want to leave with one sort of uber thought. So there is this concept called tunnel sec that we have come up with in Arista. This is an umbrella term which is basically meant to encapsulate the different types of tunneling technology, be it that IPsec, MACsec, or VxLAN sec. All these things are different aspects of how we securely tunnel traffic from one location to another location, whether it's a branch, remote site, or a campus. Typically, what we see is MACsec in campus, IPsec in remote and branch. But there is a concept called VxLAN sec. Basically, it takes a VxLAN packet and uses MACsec-like encryption, but uses an ESP header that we use in IPsec. That combination actually allows us to interconnect data centers and essentially run a VLAN between two locations. So you can have an AP in Metro A and an AP in Metro B, both on the same VLAN going through the data center interconnect.
So this is Mojo's solution to tunneling without controllers, right? If
this is Arista solution.
Says,
yes.
Well, we like your product, but we want tunneling. This is a way to say, well, we can still offer you the benefits of tunneling without. But you're just using a newer technology.
We are just using an existing technology, VxLAN, and we are just using the switch hardware because we are only using VxLAN.
So is the VxLAN sec being done at line rate using the MACsec hardware?
Absolutely. In fact, we have products today that are shipping at 100, 200, and 400 gig.
We'll talk about that in the
yes.
We will talk about that in the offline.
To my heart's content, happy to talk about it. Just 30 seconds. I know we are going past the time, so I just want to expose to the CVQ. Probably heard from other presentations. Cloud Vision Cognitive Unified Edge. Cognitive was there. What is the unified edge part of it? We are actually bringing together the edge threat management. This is the recent Untangle acquisition, as well as some private LTE parts of it. It's sort of a little bit of a forward-looking statement we are leaving with. We'll definitely come with a lot more details on that. This is the whole CBRS private LTE part of it. And today, these are the products that go under this Cloud Vision queue from a management plane perspective, and we're working more to integrate the whole monitoring plane. All that we talked about, the client journey and the monitoring and the troubleshooting and all those things, we want to bring it together for the edge campus scenario under the guise of the Cloud Vision queue.